All right, so you can see now why the doubling decomposition is important. It connects up with this, is that if I have two communicating classes, I've got a V1 here and I've got a V2 here, which are obviously different because V1 is 1 and X1, and the other ones could be 1 and X2. And so I've got repeated eigenvalues. My theory last lecture falls apart. You know, so I don't have a negotic theorem. So what else do I need? That's not enough. All right, so getting rid of that X2 is not enough. What else do I need? All right, so we know that saying only one communicating class is enough to, well, you can believe means there's a single eigenvalue at 1. It's not repeated. What else can go wrong? Periodicity. Well, actually, let's wait on that though. I just realized before I do this, let's give this a name. This has a name, another definition. Unit chain. So the Markov chain is unit chain, or the transition matrix is unit chain, whatever you want to say. It's unit chain if this is true, without the X2. Instead of calling it X1, I'm going to call it X bullet like that. So there's just one communicating class, and the same thing I've written before. So that's what we're going to stick to throughout, you know, and generalizations for general state space Markov chains. So it's exactly that. But with an additional assumption on the transient set. So it says from the transient set, there's some possibility of getting to this set. You know? Because I'm saying this is positive for all x, in particular for x in the transient set. All right.
So then the difference between unit chain and irreducible is that you can put tau into x.
Yeah, you've got this transient set as well. So yeah, that's right. And so you can see why you often when you teach this course, like if you give a course of Markov chains, you do this and you dismiss it. You say from now on, we're going to assume that x equals x bullet because this is junk anyway. It's, you know, we yeah. Yeah. And then I'll get to yours because aperiodicity is really only defined for unit chain Markov chains. Nah, one more. So it's difficult to extend this to general state space Markov chains. There's an equivalent definition which is easy to extend. So this is maybe less common in a course like this, but for general state space Markov chains, it's the assumption. This instead of having to go try to find a communicating class, you just try to find some special state and say the probability of getting from any point to that state is positive for all x. Now you look at this, you can see I could take this x dot, I could take it to be 2 or 3 or 4, any of them, right? Because this just says from any initial condition, there's some n for which this is positive. And so from 1, I can go from 1 to 2 to 4 to 3. So in 1, 2, 3 hops, I can go from 1 to 3, all right? So 3 is reachable from 1. In 2 hops, I can get to 3 from 2. In 1 hop, I can get from 3 to from 4. And from 3, I can get back to myself. All right, you got to check that too. I'm summing from 1 to infinity. So from 3, I can go to 2, and then 4, and back to 3, and get back to myself. All right. So this guy is x dot irreducible for any x dot, and the reason that's clear is because these definitions are equivalent. So if this is true, this is true. And does anybody have any thoughts on how you, the only difficulty in proving this really is the fact that if this is true, I want to prove this is true, I'd have to have some way to cook up what this set is. What do you think the communicating class would be? So under this assumption, can you imagine how you would construct a communicating class? So from any point I can get to x dot, and so I know x bullet, or whatever you want to call it, is in the communicating class. Well, what is exact? Oh, that's a good idea. You could take the union of the x bullets. That's true. You could take the union. That's hard to work with. That's a good one. Yeah. You could take the union of all x bullets such that the chain is x bullet irreducible. That's hard to work with, though. You're right, though. That does work. Yeah.
A simpler idea would be just to find all the cycles in the graph, and then you could find all the unique vertices, and those would be the x star irreducible.
Well, yeah, you could take that. You could look at all possible paths that come back to this point, and the vertices you see are define x bullet. And let me write that down. That's more what I had in mind. You can take x bullet to be the set of all y such that the sum, this is the same thing you're saying, n equals 1 to infinity, are the probably n steps going from x bullet to y is positive. That's what you're saying. Because saying this sum is positive means that there's some path going from x bullet to y. Yeah. Okay. So that's how you do it. So from any state I can get to x bullet, right? And the x bullet I can get to any state y, which is in this set. And so that's how you do it. Now I can come back to that final definition. This is it. No more definitions. Okay, so I mean, again, this is the same as this. The unit, when I say unit chain or X-study reducible, I'll only use this X-study reducible language when I emphasize that there's one particular state I'm going to pay attention to. Okay. So under the assumption of unit chain, I'm going to call it aperiodic if there's an integer n naught. And such that the probability of returning is always positive after that time. I mean, greater than 0. And it turns out this, and again, it would take a few hours to get all these details out. I'm not going to do it. I'm going to take another course. But to say that for unit chain Markov chain, to say it's aperiodic, first of all, it just means that, again, there's some time n naught, and the probability of returning to x dot after n steps is always positive after n naught. Okay, so if that's not true, it turns out there's a decomposition of the process. One way to say it is that aperiodicity is the same as saying that if I take the nth power of this Markov chain, it has a trivial Dublin decomposition, a single communicating class for each m. Another theorem, if not aperiodic, then there's another representation. You take the you take this guy, and I can't use xi's anymore. I'll call it S1 union S2 union dot 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 using SM, where again it's disjoint, and you just hop from one to another. So the probability of going from x to SM plus 1 equals 1 if I'm in the previous state. And this is all mod m. Oh no, sorry. Call this something else called capital M. So I have a disjoint union of sets, and from one set I go to the next set. So I could basically carve up my state space. This is my state space. I can chop it up. Here's S1, S2, S3, S4. And from this point, I necessarily go somewhere here. And from here, I necessarily go somewhere here. And it's really periodic. And you can imagine, if I've got this periodic behavior, I can stick an eigenvalue right in the unit circle. Same arguments I used before. And you can also see that p to the 4 has a doubling decomposition. Right? In 4 steps, 1, 2, 3, 4, I end up back where I started from. Here, in 1, 2, 3, 4 steps, I came back to where I started from. Each one of these becomes a basically, I mean, I haven't given you the details, but it becomes well, I need to give you more details about the SIs, but each one of these becomes a communicating class for the 4-step transition matrix. Okay, there's no transient set here. I'm just saying that x equals x bullets, say. Let's forget the transient set. All right, so then each one of these will end up being all right, cool. So that's what, so there you have it. So, good. So the conclusion I was trying to get to is that for the last theorem, which I won't prove, different color just so I can make this clearer. So if I have a unit chain, Markov chain, aperiodic, finite state space, then what am I going to say? then we arrive at the assumptions last lecture, which then we have this, and therefore ergodicity. So p to the n from x to y converges to pi of y as n goes to infinity for all x and y. So it's a really nice connection, and you can really see the eigenstructure and how it relates to the assumptions. Okay. So we stop now, don't we? Yeah. I was going to give an example, but we'll wait till next time. All right. Anyway, there it is. This is the classic theory you'd get in finite states as Markov chains. And what's left is to get a deeper understanding of both this Poisson equation and the ergodicity. So we can apply that. And also the sample path ergodic theorems, like the law of large numbers and the central limit theorem, which we also need for understanding algorithms. That's going to be fundamental. So that'll take a few weeks, and then we move to the next. Then we move to control. All right. Cool. Until next time.